All right, so we have already talked about how to solve equations using elementary row reduction. So I'm not going to do that again here. Let me talk about two things, two more pieces that are covered in this section that we had not talked about previously. You remember we defined a linearly independent set of functions or vectors. Okay, so suppose we have a set of vectors, let's say x super 1 up to x super n. Then these are let's say row vectors. Row vectors in xm. In Rm, sorry. So these vectors are linearly independent. Remember, for me, Li always means linearly independent if and only if summation Ci xi from I equals 1 to n equals 0 implies all the c's have to be 0. Okay. All right. So that was our definition of linearly independent functions, linearly independent vectors, set of things, whatever you want to call it, or a set of objects, is which vectors can be just thought of as objects. So if a set of vectors is linearly independent, if when you take an arbitrary linear combination of them and set it equal to 0, the only way that can be satisfied is if all those coefficients are 0. Okay, so we want a quick way to check if a set of row vectors is linearly independent, or if it's not. And if it's not linearly independent, it's linearly dependent. Okay, so how are we going to do that? Well, basically, let's write out what this means. Okay, I'm sorry, I forgot to switch that so it stays put. Let's look exactly at what this statement means. So that means if I think of each of my vectors, x super I, let's say these are all vectors in Rn. So this is an x, xi1, xi2, up to xin. Each of those components is is a real number. Okay, so I'm putting the superscript I to remember which vector it came from. So Ci times Xi then means Ci times Xi1 up to Ci times Xi10. Okay, so if I look at the sum from I equals 1 to n of Ci Xi, that is, okay, so when I do these rows, I will get C1 X11 plus C2 X21 plus Cn Xn1. I'll get all the first components multiplied by the C's and then add it up. And you keep on doing that. And at the last one, you'll get C1 Xn1, because I'm be doing this with X1, C1 times X1, capital X1. And then I'll get C2 Xn2. I'm sorry, yeah, that's 6xn2, that's right, plus cn xnn. And we want to check, when does that equal 0? Okay, that's the definition. We want to look at when does this equal 0. So this means really the 0 vector. Okay, so that means we have the unknowns here. This is what looks a little funny when students first see this. The unknowns are C1 up to Cn, because you're given your vectors. We're given x1 up to xn, and so you know all the components of x1 up to xn. So the x's are known, It's the C's that are not known. Okay. So we need to um, we need to figure out if the C's have to all be zero or not. So this is n equations. Each one of these gives me an equation. So there's 1, 2, 3, all the way up to n of them, n equations in n unknowns. Okay. So how would we solve that? We would look at the equations. Okay. So one way to do it. So let's say first method. The C's are the unknowns. So we would put in x1, 1, x2, 1, because these are what's known, xn, 1, and then it's equal to 0. And then in the next row, we would have x1, 2, x2, 2, all the way up to xn2, and that's equal to 0. That's the second row, which I hadn't written out here, but I'm writing out here. And you keep going, and your last row is x1n, x2n, up to xnn, and that equals 0. Okay, because that's how you would write this system of equations. Think of it as one, this thing equals 0, the next one equals 0. So that's n equations. So this is by our old method, and row reduce to C if C1 equals C2 equals Cn equals 0 is the only solution. If so, then x1 up to xn is linearly independent. If not, then they are linearly dependent. And that, whoops, again, okay, sorry. So you put it in, so bottom line, what is this doing? So here's the bottom line for that method. Okay, so let me try to situate this so you can see everything. So the bottom line for method 1 is you're given x1 up to xn given. How do you tell if they're linearly independent? Put them into a matrix. You put in x1, and you make, what I mean by this is I put it in as a column vector. So this is a column vector, just stick in x1. Each one is a column vector. So you put it into that matrix as a column vector. Okay, so I stick in my column vectors. Whoops, no, don't do that, sorry. Then you put in 0, 0, 0, and row reduce to see if you get the n by 1 identity matrix. So you should get ones along the main diagonal and zeros everywhere else. And this column will always stay zeros. If you get this, if you get this, they are linearly independent. Anything else, and they are linearly dependent. Okay, so that's the easiest way to do it. Okay, all right. Another way you could do that is to think of what we just talked about before. So here's a second method. We are looking to see if x times C equals 0 has a non-trivial solution where X, capital X, is the matrix where you take the given row vectors and stick them in as I'm sorry, where you take the given column vectors and you stick them in as column vectors. C is the matrix of coefficients, C1 up to Cn, and 0 is the zero matrix. Okay? So when did this system, this homogeneous system, have a non-trivial solution? This has a non-trivial solution by what we just discussed. If and only if, so if and only if the determinant of X is equal to 0. So, okay, and bottom line, a second way to do it is you form the matrix X, like I said up here. Okay, so you stick the given vectors in as column vectors. You form X. If the determinant of X equals 0, they are linearly dependent. If the determinant of X is not equal to 0, then they are linearly independent. Okay, which is faster to say, but finding determinants is not really fast. So I think the row reduction method is easier.